Hello, it's Keith here, and this is lesson 2 of the ARM Thumb assembly programming tutorials. And today we're going to be looking at the addressing modes. We're going to be discussing all of the addressing modes available to us in ARM Thumb because they are more limited than classic ARM. And we're also going to be discussing rotation because in the past rotation was kind of included in a lot of other commands. You could rotate parameters that you were using for other commands, and this was often handy with addressing modes and things. But with ARM Thumb, the rotate commands are more commands in their own right, like they would be on the 68,000. So that's changed quite a lot, and we'll be looking at that as well. So that's what we're going to be doing today. As always, you can go to my website, download the source code, and I encourage you, and it's intended that you download these and try them out for yourself, because from personal experience, I read lots of books and read all of these kind of things in books, but then you don't understand them till you actually try them out and actually put some of your own parameters in and see if what you think was going on is what really happens. Anyway, let's go over to the source code and let's check it out. So we're using the Thumb lesson 2 code today, and this has a variety of different tests that we can enable. We just remove a rem statement from one of these, and we will see each of the kind of addressing modes, and we'll see some examples of them. So first of all, we'll be trying the immediate tests. Let's just fire this up and let's see what happens on the Nintendo DS we'll be using today. So here's our Nintendo DS, and we will be looking at the immediate code examples here. So immediate addressing is just where the parameter is immediately in line with the command itself. So you can see here we've got a parameter in hexadecimal of 12. The OX means hexadecimal there, and the source is on the right and the destination is on the left. So first of all, we loaded R0 with the value 12 in hexadecimal, and you can see over here R0 equals 12 because these displays are all hexadecimal. We then loaded R1 with the binary immediate with all 10101010 there, and I guess that is AA in hexadecimal. My hexadecimal skills are not sufficient that I can remember that. I assume that's correct. And then we are loading R2 with 65 in decimal, and that is 41 in hexadecimal. So there we go. So we can load immediate values and they just go straight into the registers. Very simple. Not really too exciting, but it is an addressing mode. So we are covering it in today's lesson. The next, even simpler, register addressing. This is just where the parameter is a register. So here we've got the source is R2 and the destination is R1. So we're using address registers here. And here we are using an add command, and that uses two source parameters, both of which are registers and a destination of R0. So this is R0 equals R1 plus R2 there. And you can see here we've started off by loading R2 with hexadecimal 80. That's immediate addressing, of course, and we can see that has happened here. We've then moved R2 into R1, so R1 now also equals hexadecimal 80. And then we've set R0 to R1 plus R2. R1 is hexadecimal 80, R2 is hexadecimal 80, so R0 has become hexadecimal 100. So there we go, that's our addressing using registers as parameters there. Now what we're going to look at next is register indirect. Let's take a look at that. So register indirect is where a register contains an address, and it's that address that is the source of a parameter. Now what we're going to do here is we are going to load the register R2 with some data, which is some test data. We'll show that to the screen as well. And then we're going to load from the address in the register R2. So we're not loading from R2, but the address in R2. And with VASM at least, with ARM Thumb, if we want to load from the address in a register with no other offsets, we need to specify an offset of 0, which is a bit strange, but that's what we have to do. So you can see there's that offset of 0 here, and we'll be discussing offsets in a moment, but I wanted to discuss the typically more simple version with no offset, but we have to specify that we've got no offset in this case. So we're loading register R0 from register R2 offset by 0 effectively, and it's the square brackets that are defining that we're loading indirectly from R2 here. So we're not loading from R2, but the address in R2. Let's fire this up and see what happens. Okay, so we've shown some test data to the screen here. Here's our test data. And then we've set R2, and we've set that to the same address as the start of our range there. And then we've loaded R0 from address R2. Well, here's the data at the start here. So we've So here's the data at the start. We've got 01, 02, 3, 4, 5, 6, 7. Now we're using a little endian system, so that gets reversed. So you can see 6, 7, 4, 5, 2, 3, 0, 1, R0, and that's been loaded from the address in R2 there. What we then did is we've actually done a shift of the value in R0, changing it. We've effectively shifted its bits by 16. We'll see more about that in a moment. So R0 has changed there. We've then stored R0 back to the address in R2. The str command also can work with indirect addresses. So we've now stored that value back to the value in R2, which is the test data. So the test data started 01, 2, 3, 4, 5, 6, 7. We then stored back the value quadruple 0, 6, 7, 4, 5, and you can see now in little endian 4, 5, 6, 7, and then quadruple 0, because we stored back with that indirect store to the address in R0 here. So we stored back there. So that addressing mode can be used for loading or storing there. Now, we've kind of already used it there, but we didn't really specify an offset because our offset was 0. But we can specify numeric offsets, and this is very useful to us when we basically would set our register to point to the start of a bank of data. I often use this in my games for pointing to a bank of sprite settings, for example, and what you would do is you would then read from offset positions, and those positions would be different parameters like the X position of the sprite, the Y position of the sprite, and so on. So here, once again, we're loading register 3 with the address of some data, and we're then going to load register 0 with the address in register 3 plus 4. So we're taking the value in R3 plus 4, using that as the address that's the source of R0. And so that's what we've done there. Now here you can see the test data here, 1, 2, 3, 4, 5, 6, 7 again as before, and we've loaded R3 with the start of that range. But because we've set an offset of plus 4, when we load in R0, we are not loading in 1, 2, 3, 4, 5, 6, 7. We're loading in EFCD AB89, which is this data here, 89AB CDEF, and that's 1, 2, 3, 4 bytes offset from the start of the range, which was the address specified by R3. And that's because we've specified there R0 is to be loaded from address in R3 plus 4. That's the indirect address with an offset. Now here we've used a number here, but we can also specify symbols. We can find a symbol called var2, and that is the value of 8, and we can then load in from R3 offset by effectively 8. And this is, as I say in my example before, where maybe R3 is pointing to some sprite data. We could define sprite X as being at offset 4, sprite Y being at offset 8, and so on, and that makes our code nice and clear to read from. So we've loaded R1 there from R3 plus 8. R1 is now equal to 7, 8, 5, 6, 3, 4, 1, 2. And you can see that just there, that's what's been loaded in there because that's offset by 8. Now, the offsets do need to be relative to the amount loaded. Here we're loading 32-bit values, so the offset needs to be a multiple of 4 bytes. So we can load from 0, 4, 8, 16, but we can't load from offset 2. And this is actually hard-coded into the command because the bits of the resulting bytecode that is after it's been assembled is actually just going to be from a 0 bit or a 1 bit, for example, for 4 and 8. It's actually multiplied up by the processor, so it's physically impossible to load from address 2 if you're working with a 32-bit value. However, if you're working with a 16-bit half or a byte, then you can indeed load from the offsets, but the range of offsets that we will be able to specify will be smaller accordingly. Again, because the commands are compiling down to 16 bits, the offset size will be more limited. Another limitation is that these offsets all need to be positive, so we can't, for example, do load R2 from R3 offset by -4. If I just try that, we can just unrem this and compile. Oh dear, my compiling has failed. I've got an error saying 7-bit unsigned immediate offset out of range. So as I say, we do have a lot of limitations because of the way the commands compile down to bytes within our assembled program. So anyway, there we go. There's the indirect with offset there. What we're going to do next is another example. This time though, we're not going to use an immediate offset. We're going to use a register as an offset. So before we were specifying in square brackets R2 comma a numeric value like 4. This time we're using a register as the offset itself. So here we're loading R0 with the address equivalent to R2 plus R1. And R2 is going to be some test data again. Let's fire that up and let's see that in action. So here we go. So we've loaded R2 with the address of our test data here, which is the same as before. We've loaded R1 with the value 4. And then what we've done is we've loaded in R0 from the address R2 plus R1 here. Well, R2 equals the start of our test data range, but R1 equals 4. So we've effectively loaded from 89AB CDEF here, and you can see R0 equals EF CD AB 89 little endian, so it's become reversed. Now what we can do, of course, when we do this is we can now change the source address. Here we can add 4, so we've added 4 there, and we can load again, and our command is effectively the same, but we're now loading from a different address, so this is great for loops. So here we've loaded R0 again, but this time we're now loading from 4 along. So we're now going to load in this 1, 2, 3, 4, 5, 6, 7, 8 value. And you can see here we've got 7, 8, 5, 6, 4, 3, 2, 1, 4, 3, 1, 2, sorry, we loaded in reverse. We can then subtract 8. We've now effectively set R1 to 0 here. You can see it was 4, then it went up to 8, now it's down to 0. So when we load in, we get 6, 7, 5, 4, 3, 2, 0, 1. Well, that's back from the start of the range. So we've been able to load in from a range of varieties there by just changing our immediate value there. Now the next addressing mode we're going to be looking at is program counter relative. So this is going to be relating to the current running command of code, and in all honesty, in most cases this is going to be kind of transparent to us, and it's going to be the assembler that's going to be working this out for us. So we're going to be using some labels. We've got some data here, and we're going to specify that label plus an offset, and the assembler will work out what that offset is and will create the code accordingly. So let's compile this. And so we've got load R0 from address some data here, and when we're doing that we are loading in effectively from here. So you can see the test data here, 1, 2, 3, 4, 5, 6, 7. So we've loaded R0 from the start of that range, and you can see there again little endian, so it's reversed. We've then loaded R1 from some data plus 4, well 8, 9, A, B, C, D, E, F, and you can see that there in little endian. And then we've loaded from some data plus 8 here, and you can see again that has worked just fine. Now next we're going to be looking at shifts. These sort of aren't an addressing mode, but they kind of were before, so I decided to put them in this example just to make it clear. Now bit shifting is of course where we shift all of the bits in a register either to the left or to the right, and if you've done other assembly and you've done ARM then you'll know about them, but they've now become commands in their own right, whereas before they were part of the addressing of other commands. So we're going to look at them here. We're going to look at the different kinds of shift that are available to us, and we're going to do this via a test value. So we're loading our registers with a test value here, and we're going to show the starting position here. So we're loading in the value 800102 here, 800102. And then we're going to try a variety of different kinds of bit shift, and these will affect the bits moving in one direction or the other. So we're going to basically set R0 to R1 logically shifted left by 4 bits, and we're going to set R1 to R1 logically shifted to the right by 4 bits. So what are 4 bits? Well, 4 bits is 1 nibble, so effectively 1 digit here. Now we can shift by 1 bit, but just for clarity on this hexadecimal display, shifting by 4 bits to the left makes it very clear what's happening. Now the first time we logically shifted to the left and right by an immediate value of 4, but then the second time we logically shifted to the left and right by the value in R2, and R2 contains the value 8. So let's see what's actually happened there. Well, R0 contained the value 8000102. When we shifted that to the left logically, the new bits that were added were given the value of 0. So the new nibble that was added there when all of the digits moved 1 to the left, at 4 bits that is, was a 0. We then shifted by R2, which we'd set to 8, which is 2 nibbles. So the 2 has now shifted 2 digits to the left, and all of the new bits were set to 0. when we logically shifted to the right, effectively the same happened, only this time all the digits moved that way. So the 8 moved 1 digit when we shifted 4 bits to the right logically, and when we shifted 8 bits to the right, it shifted 2 digits, and all of the new digits were set to 0, and that's effectively what a logical shift does. All the new bits are zeros. Now, arithmetic shift to the right is designed for working with signed numbers. Now, if the top bit of our value is 1, then our number will be a negative number. And if we shift to the right logically, then we will be adding 0 bits to the top, and that will flip the sign, which we won't want to do. So arithmetic shifts solve this problem. They shift all the bits to the right, but the top bit stays the same as it was, and any new bits that are created will retain that original value. So for example here, we've shifted R0 to the right by 1 nibble, 4 bits, and you can see the old value started with an 8, which is a top bit of 1. So when we shifted to the right by 4 bits, all the new bits had a value of 1, which is an F there, that's why that's happened. And then when we shifted 8 bits to the right, all of the new bits that were created were 1s, so we've got an FF there, and the sign is now still the same. Now, the reason we might want to shift to the left and to the right like this is when we shift to the left, we are effectively doubling the value in the number. And when we're shifting to the right, we're effectively halving the value of the number. And that's a very efficient way of dividing or multiplying by 2. Now, we can use logical shift left for doubling a number that is signed, as long as the number is sufficiently small that we're not actually losing any definition when we push the bits to the left. The sign will be retained. Now, that's the arithmetic shifts. The final one that we're going to be looking at is rotation. Now, we can rotate, and this is where the bits, as they move to the right, any bit that goes over bit 0 will come back on the left. So these just go round and round in circles. So for example here, we've got the value 8001002. We've then rotated to the right by 4 bits here. And so our 2 here has been pushed off the right hand side, but it's come back at the left hand side. There's no kind of carry bit used in this case. We've then done another rotation by the value in R3, and R3 we set to 32 minus 4, and this is effectively a rotate to the left because any bits that go to the right come back at the left. So if we rotated by 32 bits, we'd actually end up exactly where we started. We'd end up with no change. So rotating by 32 minus a number is effectively rotating to the left by that number. So here we've rotated effectively to the left, and that 8 value has been pushed off the left hand side and has come back at the right. Now, it's important to notice there are some commands that don't exist. There's no official rotate left command, although, as I say, we can simulate one there, and we can't do this with immediate values in the way that we can with arithmetic shift right and logical shifts. So the rotate command is a little bit more limited, and there's no rotate command that uses any kind of carry or extend flag in the case of the thumb instruction set. So there we go. So that's how the shifts now work for us. The next one we're going to look at is the commands that work with multiple registers and the stack. Now, these commands have been heavily pared down, and to be honest, I'm not going to cry any tears about that, but we do have still one command left, or one pair of commands rather. So we've still got ldmia and stmia, and these will store a variety of registers to the address in a register. So here we're specifying to store registers ranged from R0. So here we're specifying to load the range R0 to R1, which I know is just 2 registers, but we could do R0 to R5, for example. And we're also loading register R3. Now we're specifying to load these from address R2. We do still have to specify the exclamation mark after R2 to tell the assembler that we are updating R2 after the command. So here what we're going to do is we're going to load this set of registers from the address R2 onwards, and then what we're going to do is we're going to flip the bits of those registers just so that they're changed, and then we're going to store those registers back to the address in R2. We're going to reset R2 after the first load. So if we compile this, we'll see what happens. So what we've done is we've got our test data there again. We've got R2 pointing to the start of our test data range. We are then loading R0 R1 and R3. Now, it's important to understand that the order that we specify the registers in this list isn't the order they load in necessarily. If we swap the order around, it wouldn't make a difference. The command doesn't store the order we specify, it has its own built-in order. So what we've done here is we've loaded in 01, 2, 3, 4, 5, 6, 7 here, and we've loaded that into R0. We've then loaded 8, 9, A, B, C, D, E, F into R1, and we've loaded in 1, 2, 3, 4, 5, 6, 7, 8 into R3 here. R2 we skipped there because of how we specified these here. We've then flipped all the bits and stored those values back. You can see here are the flipped bits versions here, and then we've stored those back to the range here. You can see that's happened just there. Now, the exclamation mark in this command specifies that the R2 register is updated by the command, but this is kind of a bit of a hangover from the original ARM instruction set, because if we remove that exclamation mark, say we didn't want R2 to change, well, that's not going to work. Thumb can't do that. So we have to specify the exclamation mark, even if we would actually prefer R2 to be unchanged. It's just, as I say, it's a bit of a hangover from the traditional instruction set. Now, that's how we can use ldmia and stmia to load or store registers from to or from an address in a register. Now, as with a lot of our commands, these are now much more limited to the valid range of registers we can use. So we can't use these with, for example, with register 13, and that means we can no longer use these to work with the stack pointer. This has been countered by, and I quite like this, by having a new special push and pop command which will work with the stack pointer. Now these use the register list in exactly the same way. So push R0 to R1, R3 will push all of those registers onto the stack, and pop will restore the values of those registers. Very nice. As I say, this is what I like to see personally. This is much more what I'm used to. So here what we've done is we've pushed those registers onto the stack. We've loaded some dummy values into those registers there, and then we've popped the original values off the stack, and you can see here that has indeed happened. There is our original values. We've loaded our test values of 1, 1, 2, 2, and then we've popped the original values off the stack, and you can see that that has worked exactly as we would expect. As I say, I find having a nice simple push pop command far simpler than using these kind of complex commands, which were the kind of thing we had to use with the original ARM instruction set. So personally, I think that's a very nice thing, but I'm sure some people out there will disagree, and you're totally welcome to do so. Anyway, that's all we're covering today. This is by no means the end of the ARM Thumb assembly series. We've got lots more coming. Next time we're going to be looking at branches, compares, things like that, so we'll be looking at that. As always, I have to tell you, I have a book available which covers the classic ARM instruction set. I'm afraid it doesn't come with ARM Thumb, but it also covers Z80, 650, 68000 and 8086. It's called Learn Multi-Platform Assembly with Chibi-Akumas, and it's available on Amazon. And if you buy the book, if the book's popular, there will be another book which will cover ARM Thumb, because I want to make more books if people want to read them. Anyway, I hope you've enjoyed this today. Thanks for watching, and goodbye.